Okay, well, how are you guys doing? It's Wednesday, so again, summer is fast, and so it's just the second day of class, but we're practically like it's like the end of second week now. Okay, in terms of like if you were on a regular 10-week quarter, the stuff we're covering here comes from like the second week of class. So anyway. I hope things are going okay. I hope you've taken a look at the first homework assignment, and you're gonna. Well, it's due on Monday, so you got to get working on that. Okay, let's continue and pick up where we left off. We left off, and we said, we want to take a look at linear regression. And we are going to look at it with in matrix notation. And we said, when we're dealing in matrix notation and we want to try to optimize a function, a lot of times to find the optimum of a function, you take the derivative, you set it equal to 0, and you solve. And we're going to do something similar here, except we're in kind of this multivariate setting. And so we take the equivalent, the multivariate equivalent of a derivative, we call that the gradient, okay? And we're doing basically some vector calculus here. And here's some just useful relationships that will help us calculate the gradient. And we're gonna say, all right, let's, if we wanna take the gradient of this quantity with respect to W, then we're gonna get X, and this is a little useful table. And we wrapped up Monday's lecture by saying, okay, here's our loss function. Remember, our loss function is the basically mean squared error. We take the difference between the target values and our predictions. Our predictions are found by doing W times X. And we're saying, let's take the difference of those values squared, and we expanded this out, and we said, okay, now let's solve for the W that will optimize this thing. The way we did that is we said, okay, let's calculate the gradient of this loss function with respect to W. And when we did that, we got this. And then we said, let's set it equal to 0, and we're going to solve. Okay, and this is where we left off on Monday. We said, this is the loss function in matrix notation. We're going to take the gradient of that loss function with respect to W. W, again, is the vector that contains our slope and our intercept parameters. And because we're looking for the slope and intercept that's going to optimize this function. We're looking for the slope and intercept that will minimize the total sum of squared errors, or the mean squared error here. And so we said, let's take the gradient of that loss function with respect to W. We set that equal to 0, we solve for W, and we end up with this maybe familiar quantity, X transpose X, quantity inverse X transpose T, okay, where T is the response values and X is are the values in our X matrix, okay? And right now our X matrix is, n rows, 2 columns. One of those columns is a bunch of 1s, which corresponds to the intercept, and the other column is our X values. And this is what we have, okay? So we say the estimate of W that minimizes the loss function is this, X transpose X inverse, X transpose T. So let's just apply it to a very, very, very simple data set, okay? So in this data set, I have the values 1, 2, 3, 4 for X, and our response values are 1, 3, 2, 4. So not exactly, these two values are a little, aren't strictly increasing, okay? And we say, okay, well, let's try to fit a line to this data. We want to find the line that minimizes the mean squared error for the residuals here, okay? And so we say, okay, well, let's create our X matrix. So our X values are 1, 2, 3, 4, and we're going to bind a column of 1s to it. So this is my X matrix. So it's 4 by 2, n by 2. And then we'd say, okay, well, what is X transpose X? Okay, if you have an n by 2 matrix and you do X transpose X, you're going to get a 2 by 2 matrix, right? This is our X transpose X. when you we'll do remember we're doing X transpose X inverse X transpose T. So we take our 2 by 2 matrix, we're going to calculate the inverse of it. Okay, the way we calculate the inverse in R is we call solve. Solve on the 2 by 2 matrix, and the inverse of a 2 by 2 matrix is also a 2 by 2 matrix. Okay, and these are the quantities here. So we have 4, 10, 10, 30, and then if we were to multiply this 2 by 2 matrix with this 2 by 2 matrix, we would end up getting the identity matrix, right? So that's so we do that. So this is the inverse of X transpose X. Then I do X transpose X inverse times X transpose, and that results in a 2 by n matrix. And then I multiply that finally by T. T is all of the response values. Okay, we have n values. It's a column, a single column. So n by 1, it's these numbers, 1, 3, 2, 4. So n by 1. And so when you multiply an n by 2, 2 by n by an n by 1, you get the result is a 2 by 1. Okay. So W hat is 2 by 1, and this corresponds to the intercept of 0.5 and a slope of 0.8. So that's what we get. If I were to say, hey, let's just take X and T and then let's just do LM. So we're familiar with the LM function in R. And indeed, LM says, yep, the values that's going to give us the linear model, the intercept and the slope is going to be intercept of 0.5, slope of 0.8, which is exactly what we found by doing the operation X transpose X inverse X transpose T. Okay. So how do we get our predicted values? Okay, our predicted values are just found by doing X times W hat, right? So W hat is this 2 by 1 matrix. X is this n by 2 matrix. So I can do the n by 2 matrix, X times W hat, and I get an n by 1 matrix. And these are all of our predictions. So we can see this first one is 0.5 and 0.8. And so if I do 1 times 0.5 and 1 times 0.8, and I add those two together, I get 1.3. So we're just doing X, the X matrix, column of ones, our values 1, 2, 3, 4, times W hat, which is 0.5 and 0.8. So the next one is 0.5 plus 2 times 0.8. So 2 times 0.8 is 1.6. And we get 0.5 plus 1.6, 2.1. And basically these are our predictions, right? 1.3, add 0.8, 2.1, add 0.8 to get 2.9, add 0.8 to get 3.7. So we can see that linear trend. And I can plot that, right? So these are the values as predicted by the line. So intercept of 0.5, slope of 0.8, this red line shows our linear trend, okay? Where the actual values are 1, 1, 2, 3, 3, 2, and 4, 4. And so that's what we have for this very simple toy data set. Okay, let's take a look at the Olympic data set. The Olympic data set, our X variable is the year in which the event was held, okay, or the Olympics were held. So we have, 1896 and 1900 and 1904 and 1908, so on and so forth, up to 2000, what is this, 2004, 2008, 2012, okay? And there have been a few more Olympics after that, the 2016, 2022, and our 2020 Olympics, and, well, I guess 2020 Olympics were delayed till 2021, but I think they're still considered the 2020 Olympics. But anyway, this is what we have. These are our Olympic data, and we can say, okay, well, let's try to find the line. Okay, we want the slope and the intercept that best fit this data. Okay, so I can just kind of cheat and peek ahead and say, what should my intercept and what should my slope be? And so I can just say, all right, take the time column and predict the time column using the year column. And so I'm going to just use LM, and when I ask what's the result, it says the intercept is 36.3 and the slope is negative 0.01328. Okay, so basically every year that goes by, we expect the winning race time to drop by a little bit more than 1/100th of a second. 0.033 basically, okay? So every year that goes by, we expect the winning race time to drop by a little bit more than 1/100th of a second, okay? And we can say, okay, well, let's try to do our matrix operation here, okay? So for our matrix operation, we need our X matrix. The X matrix has a column of ones that's going to correspond to the intercept. And then we have a column for the X values. Here, these are the years. 1896, 1900, 1904, 1906, so on and so forth. So we have our X matrix going on here, okay? And then what do? We are going to do X transpose X inverse, X transpose T, okay? So I say, all right, do X transpose X inverse solve times X transpose times the value that I'm taking the time column and I'm making a matrix out of that. And what do we get? We get 36.309 for the intercept, 36.309. And the slope is negative 0.01327532, which matches exactly negative 0.1328. Here we see that, if we keep a few more decimal places, it's actually 753. So these coefficients match the results that we get from LM. So far, it's looking good. It's looking good, this method of doing kind of matrix notation. And again, we can kind of plug in, we can do X times W hat to get all of our predicted values. And we can see as time kind of goes on, the time winning race time, expected winning race time drops. And I plot that, and this is kind of what the line looks like, okay? And we go, okay, that seems like a reasonable fit to the data. Okay. So that's simple, that seems straightforward. That's how we do linear regression. Before I forget, let me go ahead and give you your first view quiz answer for today. Week 1, Wednesday, question number 1, the first one is the letter E. E as in elephant, E. E as in elephant is your first view quiz answer, E. Okay, a non-linear response from a linear model. So we can fit non-linear shapes even though we're using a linear model. Basically, we can take our variable year and we can add little transformations to it. We can kind of square it. We can take the log. We can do all kinds of stuff and create basically new variables based off of this variable, and then but we'll still combine them in a linear fashion. Okay, so let's say we wanted to fit a quadratic model. So we can still perform least squares regression, and all we will do is we will expand our X matrix. So my original X matrix was just the column of ones and the column of X values. And here I can create a third variable or a third column, or I shouldn't say third variable, a third column here by just taking this column and just squaring all of the values. Okay, and we'll still kind of do least squares regression, and this will still be a linear model, okay, because we're just going to multiply the first column by a constant, add the second, take the second column, multiply it by a constant, and add the third column after multiplying it by a constant. So the three columns are still being combined in by multiplying by constants and adding them together. It's just that this third column is related to the second column in that it is this second column value squared, okay? But effectively, it's still a linear model because we're just taking the different pieces and we're adding them together after multiplying them by a constant. Okay, so if I were to do this, I can just take a column of ones, column for X, and then I'm going to take my X values and I'm going to square them, okay? And then I'll give column names, and this is just the first 6 rows. So if I do, I get 1, 1896. 1896 squared is, I guess, 3,594,816. 1900 squared is 3,610,000, and so on and so forth. And so these are our squared values here. Okay. If we think about what is the value that is being predicted by this now larger linear model, where I'm doing, I have three coefficients to estimate, W0, W1, and W2, okay? If we look at this, this is still the same. If we were to express this in matrix notation, we're still going to just say it's W transpose X. Okay, it's just now W has three terms in it. Okay, and X has three terms in it. Okay, it's a 1, an xn, and an xn squared. But we have three terms in this X vector. Okay, so the this thing has gotten bigger, but in matrix notation, we have basically the same thing. It's just W now has three values in it, and X now has three values. Okay, so so if we look at, what does our what are our predicted values look like? Our predicted values is the matrix X, which is now expanded with three columns, our vector W, which now has three values, but really our predicted values are still just X times W. Okay, and that's kind of the beauty and the reason why at this level in kind of machine learning, we much prefer working with matrices, okay, and doing a lot of stuff in matrix notation rather than doing kind of just individual values, right? So there's kind of, you're used to probably regular algebra where you just have, the intercept and the slope times x, and then you can say, okay, well, we want to add a third term, okay? But what if we want to add a fourth term or a fifth term or a sixth term? This thing just keeps getting bigger and bigger and bigger and bigger. Whereas if you say we're going to work in matrix notation, which admittedly is a bit of a hurdle in the beginning, but once you're in matrix notation, everything kind of stays the same, even though you're increasing the dimensionality of your x variable, okay? Because it's still just x times w, okay, in this thing, right? And that matches exactly what we want. And therefore, when we say what is the loss function, okay, this is the loss function that we had when we just had two values in w. But you know what? It's the exact same loss function when we have three values in w. And it's going to be the same loss function if we have a linear model with 17 columns or 200 columns. It's all the same, okay? It's all going to be t minus xw transpose, t minus xw, okay? Times 1 over n to get it to be the mean squared error. All right, so by using matrix notation, we can add additional terms, add additional columns in our X matrix, and this formula for calculating the loss remains exactly the same. And therefore, all of the steps that we went through where we expanded this in matrix notation will be exactly the same. If we take and we say, hey, let's take the derivative, or I'm sorry, the gradient of this loss function with respect to the vector w, set it equal to 0 and solve, we're going to end up with the exact same result, okay? W hat is equal to x transpose x inverse x transpose t, okay? Whereas if we had approached this kind of the other way, using partial derivatives, now we would have a system of three equations to solve, right? We would have the partial derivative with respect to w0, the partial derivative with respect to w1, the partial derivative with respect to w2. I got three of these things. We're going to set them all equal to 0, and I have to solve all of these things simultaneously, and that's going to be a pain. With 4 things, it gets even more complicated. 5 things, it gets more complicated. And so this is why we prefer to work in matrix notation. It just keeps things simple. Once you make the jump to matrices, it's hard to go back, okay? Because you say, well, it's exactly the same, all right? X transpose X inverse X transpose T. It's just here my X is now n by 3, okay? So X transpose X inverse is a 3 by 3 matrix, okay? But it still just simplifies down to a vector, okay? A single vector, and this is going to be a 3 by 1 vector here, W hat. So let's try to solve this in R. Okay, so I'm going to take my X matrix. So my X matrix, I think there's 28 rows, and I've got 3 columns. Right, so I created this way back here. Okay, so I've got my column of 1s, column of x's, column of x squared values. But I run into an error. So if I say, okay, do X transpose X inverse solve this, and multiply by X transpose times the values t. Okay, so this is the same command that I ran back here. X transpose X inverse solve X transpose X, X transpose this matrix Olympic time here, and I got my W hat and it worked there. When I do it here, I ran the exact same code, and now I get an error. I get error and solve.default system is computationally singular reciprocal condition number. Okay, what do you think is going on here? What does this even mean? Solve.default system is computationally singular. Okay, so it's saying there's a problem in this operation of solve. Okay, when I'm trying to do X transpose X inverse, I'm running into a problem here. Okay, and it's basically saying I can't calculate the inverse of this matrix. Okay, which is a real thing. Sometimes there are matrices that you can't calculate the inverse of. Okay, but this is not really what's happening here. Okay. And so if I look at X transpose X, because this is what I'm trying to find the inverse of, okay, so X transpose X gives me this, and if I'm trying to find the inverse of this, it's telling me there's a problem, okay? And you can actually take the inverse of this matrix. It's just my computer can't, okay? Well, if I show you X transpose X, can you see where the problem might be when I ask for it to calculate the inverse here? What's that?
The rank might not be 10.
It's not so much a problem with, well, I mean, I guess the computer sees it that way. The problem is that this number down here, E plus 14, is a really big number, okay? It's a really big number. And I don't know if you took 102A with me or not, but if you took a different 102A class, did you guys talk about like floating point arithmetic and the limits of your computer? Okay, so in floating point arithmetic, which is how our computers work with numbers, okay, they're not real numbers, okay? The computer, you know, we work with decimals and we add and subtract fractions and things like that, and it feels like real numbers, but they're not real numbers. They're like approximations to real numbers, right? It's just kind of like when you write 1/3 in decimal form on a piece of paper, you can't write infinitely many 0.333333. You just cut them off somewhere. And that's not the equivalent of 1/3. It's just an approximation. So basically all the numbers inside your computer are approximations. And there's a limit. There's an upper limit to how big your numbers are. And there's also a limit to how big you can have one number and add on a small number, right? So if you have a really big number and you try to add on a really small number, your computer is not able to do it. It doesn't see the difference. Like if you have like 10 to the 16 and you try to add 1, it's not going to be able to add 1 to 10 to the 16, okay? It's going to just say, oh, you add 1? I'm still exactly 10 to the 16. It's not 10 to the 16 plus 1. It's just exactly 10 to the 16 because the computer is just not able to see that kind of difference. And so when we try to inverse this, okay, right, when you do something like X transpose X and you have the year 2000 and you square the year 2000, you get 4 million. Okay, and then when you take the entire thing and you add that all up, you get these really big numbers on the order of, 10 to the 14, okay? And then, finding the inverse, okay, requires us to kind of multiply by the constant, which is 1 over the determinant. And what happens is when you try to inverse this thing, you get a really, really, really tiny number, okay? A really, really tiny number that ends up being smaller than the machine epsilon, okay? And so the computer is not able to, no longer able to kind of compute these numbers and add them up properly, right? So we run into this computational instability, and then the computer says the matrix inverse doesn't exist, and that's actually not true. The matrix inverse does exist if we were able to work in real numbers, but we're not working in real numbers. We're working in, fake floating point numbers, and so so the computer just kind of crashes. Okay, so these are some of the things that you can run into when doing kind of machine learning stuff, especially if you have really big data sets, or just big numbers. You have to be aware that most of the time you're working in floating point numbers, and then there are real hard limits on how much computation your computer can do. So here's just a simple workaround, okay, is we're going to take that number and then I'm going to square it. So 1900 squared, is, what is it? 3,610,000. And I'm going to just say, you know what? Rather than 3,610,000, let's just multiply everything by 0.0001. So I'm going to get 361.000, okay? And so these are all just like, it's basically the exact same information, it's just I've made them smaller, okay? And now if I say, hey, take this matrix, do X transpose X inverse and solve, it works, okay? So the computer is able to calculate take this matrix, do X transpose X and then calculate the inverse of that. So it works. So it's just this computational problem of having some really big numbers and really small numbers, and trying to divide by a really big number, which produces a really small number. So that's a workaround, okay? And so I can just say take this. Do X transpose X inverse, X transpose, and times T. So I called this matrix X scaled to kind of say this third column has been scaled by dividing by 10,000 or multiplying by 0.0001. And what do you know? It works. Okay. So that's so this is now my intercept, my slope, and this is the coefficient associated with x squared after multiplying it by 0.0001, okay? All right, and so if I were to ask R to do LM, so when you ask R to do fit a linear model using LM, it doesn't do this matrix operation. So we can do X transpose X inverse X transpose T, but when you ask R to use LM, it actually doesn't do the operation. It does something entirely different. I'm not entirely sure what it does underneath the hood, but it does something different, but it gets the exact same values that we got, okay? And so again, this is just fitting my scaled matrix, not the original matrix, okay? Here I have a 0 plus. The 0 plus means, tells R I don't want to fit an intercept term, okay? Because the intercept term is accounted for in the first column, okay? Right, the first column is just ones, so we don't need to fit a separate intercept term. If I try to fit the intercept term and the first column, then we're actually going to get a problem, because the two values, the intercept and that first column, are exactly collinear. So we run into a problem, right? You can't have columns that are exactly derived off of each other. Okay, and then here we'll do calculate the fitted values. We take our scale values, multiply by the W hats that we figured out. We get our T hat, and we'll print this out, and then we can graph it. And here's the fit, okay? And we look at this and we go, oh yeah, that looks pretty decent too, okay? So it's kind of funny. I feel like our brains can be easily influenced, because if I look at this line, I say, yeah, that looks pretty good, right? And then if we look at this line, I think we go, Yeah, that looks pretty good too, right? Even though they're like very different, I think just our brains can kind of be easily influenced by just the drawing of a line, and we feel like, oh yeah, that looks pretty good also. And you might wonder, like, okay, well, can I fit? That was a quadratic line. Okay, what if I fit a cubic polynomial? What if I fit a fourth order polynomial and things like that? And we can do that. There is a function in R that makes our life a little bit easier. It's called poly, and it creates polynomial, matrices of polynomials of higher degree. But one of the issues is that when you have, if you just took your values x and then you squared them, and then you raise them to the third power, and you raise them to the fourth power, you run into a problem where they're all highly correlated. Okay, so let me just, I don't even know where to draw over here. Okay, so here if we have, say, x, x might look something like that, okay? And then if I do x squared, I might get something that looks like this, okay? And then if I do x cubed, I'll get this, and then x to the fourth will become something like that, okay? And so on and so forth. And what it is just all of these values are just super highly correlated, okay? If you calculate what's the correlation between x squared and x cubed and x to the fourth, they're all going to be like 0.9 something, okay? You're going to have these very highly correlated values. And so what poly will do is it looks at the range of values. So just on this particular range of values, so you have this kind of this linear model for y equals x, and it just says, okay, if your range of values goes from here to here, when you fit the quadratic component, it's actually going to kind of just shift the values a little bit, okay? So therefore, within this range, from here to here, and you calculate what is the correlation between x and x, the quadratic, the correlation there is 0, okay? And similarly, when you fit a cubic part, just for this range, okay, it's going to fit something like this, okay? And so within this range of values, the correlation between the cubic and x and the quadratic, the correlation between these things is all 0, okay? Obviously, if you extend past the range and you keep going down here and you keep going on forever over here, you're going to have high correlation between x and x cubed, right? You're going to have high correlation between those if you keep expanding outside of this range. But within the range of values that it sees, there's no correlation, okay? And that way, when you fit the components as determined by the by this poly thing, you can kind of isolate the cubic part or isolate the quadratic part, rather than, if you just kind of fit all of these things here, you have this, high problem with like multicollinearity. And now it's like, okay, this cubic line, am I fitting the cubic component, or is like the quadratic part getting kind of mixed in there or something, just because there's high correlation, right? So we understand that. Do we all take 101A, and we learned about the problems that when you have variables that are highly correlated with each other, your coefficient estimates are unstable? Maybe we learned that, maybe we didn't. Okay, but anyway, that's a thing, right? So if you have a whole bunch of variables that are highly correlated with each other, based on what in one random data set, you might say like, okay, variable x1 is the most important, okay? And variable x2 is not important. But if they're highly correlated, just because of like little random fluctuations in the data, you might take another random data set and it might say, okay, x2 is actually the really important variable and x1 is less important. So you get this kind of this fluctuation in things. And that's kind of a problem that we have here when everything's highly correlated. So by using poly, it kind of creates these uncorrelated versions of stuff, and that helps us kind of avoid some of these issues here. But unfortunately, the interpretation gets all weird and wonky because it's just scaling all of the values and it's kind of moving things around, and so we lose a lot of like, okay, this is the linear part and this is the quadratic part, but it's hard to I don't know where this number actually came from. So again, it just kind of scales it just on that particular range of values here. Okay, but here I'm going to say let's take the time variable, and here I'm just going to go ahead and use LM because it's going to give us our coefficient estimates, and here we get the coefficient estimate for the intercept, and x poly 1 is going to be the linear component, and x poly 2 will be the quadratic component. Okay, and so again, because it's all scaled and kind of weird stuff has happened with the poly, I'm not actually going to worry about the actual interpretation of this number -2.5 and this number 0.54. Okay, all we're going to say is, okay, well, there's a negative component, there's a positive component, but we can say, okay, well, these are the things, and I can say, okay, what are the fitted values? Okay, so when you fit LM, one of the values that shows up in the output, okay, in the list of outputs, is that it gives you kind of the predicted values, and we can just kind of plot the values, and they would be exactly these same values here. So if you look at these fitted values, 11.322, 11.228, and I go back to the values that we fitted, 11.322, 11.228, they're exactly the same. Okay, so when we fit this using, I guess my X transpose X inverse, even though I scaled it, we got these are our predicted values. And here I'm fitting it using poly, and these are the predicted values. We're getting the exact same predicted values. Okay, and this is just to say we're fitting a quadratic model here. Okay, and I wrote, an unfortunate side effect of using poly is that all of the X values do get transformed, so the interpretability of these coefficients, again, these coefficients here, -2.5 and 0.54, is dramatically reduced because it's no longer like there's not a direct relationship to the original X, okay? But using poly is still useful because we can kind of compare polynomial fits of different orders. We can say, what is the third order polynomial fit or the fourth order polynomial fit? Do you have a question? So poly is useful, I would say, in kind of this exploratory phase of fitting models where you want to fit, say, polynomial models of different order, and just to see if that's going to improve your fit or your kind of performance. And so rather than having to kind of manually take your column of values and then square them and cube them in fourth order and things like that, poly will kind of do it automatically for you, and so it's useful in that regard there. Okay, and so that's exactly what I do on this next part. I say, I want to try fitting a cubic model, a fourth order model, a fifth order model, a sixth order model, and I can do this really easily without having to manually take this column of X values and square them and specify a different model. All of these things, I basically just cut and paste all of them, and I just said, hey, predict time based on X, but do it third order, do it fourth order, fifth order, sixth order, and so on, so forth. And I just say, hey, do a linear model, fit this, and we're going to save it as the poly 3 model, the poly 4 model, the poly 5 model, right? So this just made it really easy to kind of try out a whole bunch of different polynomial models of different orders without having to, like, again, do a bunch of kind of manual work here. And so now I take all of those models and I'm going to just plot them. I'm going to just take the polynomial model and I'm just going to plot the fitted values, okay? Poly 3 model fitted values, poly 4 model fitted values, poly 5 model. So I'm going to just say, hey, what values did it predict? And they're all going to be on the next thing, and so I'm going to have a red, orange, green, blue, purple, and gray line. And this is what we have. Let me zoom in a little bit. I don't know if this is okay. And so, I mean, it's kind of cool. You know, so the red line is the linear model, and then I think the yellow line is the quadratic, and the green is cubic, and the fourth order and fifth order. And you can see they're all, as the polynomial order gets higher and higher, they all try to accommodate this one outlier from 1896 where the winning time was 12 seconds because we didn't have accurate stopwatches and things like that. So, you know, perhaps, you know, keeping that in mind, maybe we should just remove this one data point. I don't know. It seems to be kind of having a little bit too much influence on your data, right? So when you think about your outliers and the impact that they have. But anyway, and we can say, well, I don't know if any of these things actually do a great job, and especially like relationships where, you know, towards, you know, we see this sharp bend down, okay? Does that mean like in the future years, like the race times are going to dramatically improve? Probably not. But you know, this is the plot of all of the different models that we have tried fitting here, okay? The linear, quadratic, cubic, fourth order, fifth order, whatever. Okay, let me give you your second view quiz answer. Second view quiz answer today is the letter A. A as in apple. A as in apple is your second view quiz answer, A. So that's the plot, and then we can ask, okay, well, here are all of these different models that I fit. I tried fitting a second, third, fourth, fifth, sixth order polynomial, and we can ask, what is the best fitting model? Which model should we use, right? And so your kind of classical approach, you would take like, and I think you probably did this a lot in Stats 101A in your linear regression course. You would take the model that you created. So here I have poly 3 model, and then you'd say, give me a summary, and it gives you all of the coefficients. So we have the intercept. This is the coefficient for the first term, the linear component. This is for the quadratic component. This is for the cubic component. And then we would say, all right, what is my p-value associated with these things? And we get all of our p-values here are significant. And we go, okay, well, maybe all three of these things are important. And you can look at other things like your R-squared values, and you might also look at like the AIC or the BIC to try to determine what's a good fit, okay? You guys remember AIC, BIC? What are these things? What are these things? Breaking my heart. Yeah. Okay, yeah, so they're a criterion that we can use to measure how good our fit is. And what they include, so you know, the kind of the basic rule is like better R squared is like better fit, right? Overall, okay? And higher R squared means more of the variation in the output is captured by your predictors. And so when you have like a R squared of 0.99, you're saying I'm capturing 99% of that variation in there, okay? But we also know that just by including more and more predictors, we can always tweak our R squared to get higher and higher and higher, okay? And so what the AIC and the BIC says, well, hold on. We're gonna introduce a penalty for every additional predictor that you use, right? So if you're gonna increase the number of predictors, the amount you gain in your like R squared basically has to overcome the additional cost, right? So it's kind of like, I don't know, you're thinking of like cost to benefit ratios, and you can say like, okay, I can spend more money and I don't know, you got a bicycle or something, and you can say I can buy this new wheel that's lighter weight, okay? And then they sell this more expensive wheel that's even lighter weight, and this one that's even, and you can spend way more money and you're gonna shave off a few more grams on your bicycle, which depending on how competitive you are, maybe that's a big deal or something. But at some point you gotta go, I don't know, is it worth the extra cost to get the savings? And that's basically what AIC and BIC says. You're gonna get better performance, but is it worth that extra cost? And one of them, your component is like log, and the other one is like 2 times, anyway. That's what we have. So here is the summary output when we have the 6th degree polynomial, okay? And we say, okay, we're looking at all of the different components, linear, quadratic, cubic, and so on and so forth. And these ones are significant and these ones aren't significant. So maybe that just means the 3rd order polynomial is the one that we want to kind of go with, all right? And that's kind of, that's where we left it in, I think, Stats 101A, okay? At least that's what I'm assuming. I haven't taught Stats 101A in like many years, so that's what I'm assuming is covered in the classes. And this is basically what we know is that, if we only look at the R squared value, then the more complicated models are the ones that are going to get selected, because they're more complicated models will always kind of outperform the simpler ones, okay? But we have to kind of take into account things like the summary tables and are these things statistically significant and so on and so forth. And so what we're going to do is we are going to measure and evaluate our model performance and use cross-validation as a tool for selecting which model to use. Okay, so rather than taking the classical approach, the machine learning approach for model selection is to use cross-validation, and cross-validation is kind of the catch-all answer for how do we pick which model, at least from a machine learning perspective, okay? And so, again, kind of the classical approach requires us to kind of think about the variables, and it requires us to actually have knowledge about the variables. And you have to kind of ask, like, does it make sense for the winning race time to have a quadratic or a cubic relationship to time, okay? And that gets really weird, because as far as my brain goes, it's hard for me to think beyond like quadratic relationships to time, because you have like acceleration is like a quadratic relationship to time. It's like meters per second squared, and I can kind of understand that. And then you have, I guess, what is it? Jerk is the 3rd order relationship to time, and like I kind of understand that. That's kind of like the that feeling you get when like the elevator starts moving, right? The acceleration has changed itself, and so you get that change. But then it's a little bit like, what is a 6th order relationship to time? And that's like harder to answer, okay? And harder to think about. And again, we have these classical tools. Cross-validation removes this kind of having to think about the variables, okay? And you might consider this to be skillful thinking about variables, but it's also, it might end up being just arbitrary thinking about variables, and removes that from the decision-making process. And it just says, hey, these are going to be the steps that we're going to use. We have this validation strategy, and for better or worse, this is how we pick models using machine learning. So kind of one of the complaints, but also one of the strengths of machine learning is that there's less human decision making, okay? So less kind of thinking about stuff and just kind of like trusting the process, trusting the rules that we set up, okay? And so if you trust this process, if you trust the algorithm, great. But if you feel like, ooh, I don't know how I feel, then that's a valid criticism, okay? So what we do in cross-validation is we take our observed data and we split it into two parts, a training set and a validation set. Some of you are enrolled in my 101C class at the exact same time, and we just met I don't know, and 2 hours ago or something, and we talked about the exact same thing here. Also cross-validation in that lecture, but it's important. So we have a training set, we have a validation set, and what we do is we use the training set to fit our model. Okay, so as far as linear regression goes, what fitting the model, it just means figuring out what to use for your intercept and your slope, or your W2. What values do you use in your W hat? Okay, so that's going to be how we use some of the data. Okay, we call this the training set, and we fit the model to this training data, and we say, okay, for this data that we have, this is the best slope and intercept and W2 values and things like that. Okay, and so after we fit the model using that training set, we say, okay, here's the line of prediction. Okay, here's the estimated parameters. Okay, now make predictions on the validation set. Okay, so here's the validation set. Let's measure the error between our prediction line and these actual observations that we have. Okay, remember the validation set are actual observations, and we're going to say, okay, let's look at these things. Let's measure how good our predictions are. Okay, and so we use some kind of metric to measure how well our model performs at making these predictions. Common choice is mean squared error or root mean squared error or something like that. We do this for all of the possible models, and we compare the metrics for all of these models, and from that we choose the best performing model. Okay, so one strategy is leave one out cross-validation. Okay, leave one out cross-validation takes the training data and all of the available data except for one is used to fit the data or fit the model. Okay, and then we take the model that we fit and we use it to predict the one observation that's been left out. Okay, and so every data point will have a turn being kind of the validation set, being the validation point. Okay, and so if you have n observations, so if you have 800 observations in your training data, okay, you're going to fit the model to 799, and you'll predict one. Okay, and then you do it again, but this time you leave a different observation out. So you have 799 observations, and you have a different one that you left out, and you try to predict that one. Then you do it again, 799, you leave a different one out, and you try to predict that one you leave out. Okay, and you do this 800 times. Every single observation in your data set gets a turn at being the one that was left out, and you predict it every single time. Okay, so I'm going to do this process and for our toy data set where I have 4 observations, and so leave one out cross-validation. We have 4 observations. We're going to fit the model to 3 observations, predict this one. Okay, then we're going to fit it to these 3 and predict this one. Then we're going to fit it to these three and predict this one, and then we're going to fit it to these three and predict the fourth one. Okay, we're going to do this process 4 times. Each time I'm going to fit it to 3 observations and predict the one that was left out. We've got 4 observations in total. Okay, so again, my very, very, very simple data set, 1, 2, 3, 4 for x, and t is 1, 3, 2, 4, okay? And I'm going to start by leaving out the 4th observation. I'm going to say the total kind of squared error so far is nothing, and every time I run it, I'm going to add whatever squared error is. And so for training, I'm going to leave out the 4th observation, okay? And that 4th observation will be my validation thing, okay? So here is all 4 data points, 1, 2, 3, 4, and this is, if we had all 4 observations, this would be the line that I fit, okay? But again, what I'm going to do is I'm going to start by taking this 4th observation. It's like I'm going to cover it up, and now I'm going to say, okay, with these 3 remaining dots, what is the best fitting line? So if I cover this up and I say, what is the best fitting line for these 3 dots? This is the best fitting line, okay? The best fitting line for these 3 dots, the line that's going to minimize the sum of squared errors just for these 3 observations is 1 plus 0.5x, okay? And then I say, okay, here is my prediction line. Let's bring back that 1 observation I left out, which was at 4, 4, okay? So I bring that back in, the observation at 4, 4. Can you guys see this okay? So this one's now in red. And we're going to say, okay, what is the error between what my prediction line created and what the actual value is, right? So the prediction line predicts 3, and the actual value is 4, so I have a distance of 1. And if I square that, my squared error is 1. Okay, so that's the first observation. Okay, now I'm going to look. Here's the process I do. Predict t based on x just on the training data. Now make a prediction using my validation x, and then take the difference between my prediction using t hat and the actual validation point, square it, and add that to the total squared error, update our total squared error. So it started off as 0, and basically this thing is now 1. My squared error here is 1. We're going to add that. So my total squared error so far is the number 1. Okay. Again, here is the original 4 data points. I'm going to remove this data point at number 3. I'm going to say, okay, based on the remaining 3 data points, which is here, here, and here, what is the best fitting line? Okay. So this is the best fitting line. And then we're going to plug back the observation that I removed here at 3, 2, okay, which is right here. And I say, okay, what is the difference between the actual value and what the line predicted? The line predicts 3.2857, okay, based on these 3 dots in black. The best predicted value is 3.287. The actual value is 2, so my difference is 1.2857, and if I square that, my squared error is 1.65. Okay. So far, so good? This kind of makes sense? Okay. We do the same thing. This time, I'm going to take this point. I'm going to basically cover it up, and I say, okay, what is the line that best fits the remaining 3 data points? And this is the line that best fits those 3 data points. I bring back the point that I threw away, or I hid, or left out, I should say. I leave one out, bring it back, and I say, okay, what is the difference? This difference is 1.28. We square it, we get 1.65. And finally, we do the same thing. This time, we're going to leave out this one. Okay, what is the line that best fits these 3 data points? This is the line. We bring back the one that we left out. We say, what is this difference? The difference is 1. We square it, we get 1, and we add them up, okay? So if we add up all of the different squared errors, which was 1, 1.6, 1.6, and 1, we get 5.306, and the average, the mean squared error for all of these 4 different things is 1.326. That's my cross-validation error. Leave one out, cross-validation error. okay? There is, so this, I went through the process manually and I got this number. There is a function in R that will do this for us, okay? So you can call library boot. Library boot has cv.glm, and so you can fit a model. So GLM is very similar to LM for fitting your linear model, but it's generalized and it can fit things like logistic regression and things like that. And so here I have all of my data. I fit a general model to all the data, and then I just call the function cv.glm. We're going to try doing it on the linear model, and then and it says, oh yeah, your leave one out cross validation is 1.326531. Okay, which is exactly what we did when we did it manually. Okay. I went through the leave one out cross validation process for this toy data set where we had only 4 observations. Okay, and basically you get a cross validation score when you for a particular model. Okay, so here I'm basically fitting a linear model to the data, and they say, what's my cross validation score? Okay. The cross-validation score is just one value, which is the average of all of the individual squared errors. Okay, so we get a squared error for each data point, and the average of all of them is going to be the one cross-validation score that we get for a linear model. Okay, so at the end of the day, you're not going to worry about this one has a 1, and this one has a 1.6, and this one has a 1.6, and this one has a error of 1, okay? You don't worry about the individual things. You just say, overall, this linear model has a cross-validation score of 1.326, okay? So I said this required us to fit the linear model n times. We produced n different cross-validation error values, but then the overall cross-validation score is just the average or the mean of those n values. Okay, so again, just kind of the picture is for this one being left out, our squared error is 1, our squared error is 1.6, squared error is 1.6, and our squared error is 1, okay? And so after fitting the linear model to our data n times, our cross-validation score is 1.36. And then what we might want to do is we might want to try an entirely different model. We might want to try a polynomial model, or we might want to try, say, a log-log model, okay, where we do a log transformation to the x and a log transformation to the y. That's a log-log model or something like that. And we would do, we would fit that model, n different times, find the validation error for each of those instances, and then we'll take the average. And then we would get a cross-validation score, overall cross-validation score for the log-log model. And we would get an overall cross-validation score for the polynomial model. And after you fit several models, and each of them gives you a cross-validation score, you can compare the cross-validation scores, and that will help you decide which model is the one you want to use. Okay? We get an idea of how well the model predicts values that were not part of the training data. Okay. Is that feeling okay? So that's leave one out cross-validation, where we leave one observation out at a time. There's some downsides to leave one out cross-validation. And one is that it is computationally expensive. If you have a big data set with, say, 100,000 observations, leave one out cross-validation requires you to fit your model 100,000 times, okay? One for every single observation. So if you have big N, you've got a very expensive process, okay? Another kind of downside to leave one out cross-validation is that all of the fitted models end up being very similar to each other. And so your coefficient estimates also end up kind of highly correlated. You could also kind of overfit the data, okay? So an alternative, and this is generally the recommended method in general, is to do k-fold cross-validation. In k-fold cross-validation, you take your entire data set and you split it up into k equally sized, or as close to equally sized chunks. Okay, so if you have 1,000 observations, you might do 10-fold cross-validation where you have chunks of 100. Okay, or you might do 5-fold cross-validation where you have chunks of 200. Okay, and during each fold or each run in this k-fold cross-validation, one of those blocks will serve as the validation set, and then the remaining observations, the remaining blocks, combine to form the training data. Okay, so if we said we're going to do 4-fold cross-validation, we take the entire data set, divide it into 4 chunks, and we would train based on these 3, and we would validate on this one. Okay, we would do it again, and we would train on these 3 and validate on the second set, and then we would do it again, and we would train on sets 1, 2, and 4, validate on the third, and we would do it one more time, and we would train on these 3 and validate on the fourth set. Okay, each of these would be considered a fold. So 10-fold cross-validation, you're going to train on 90%, validate on the last 10%, and you would repeat that process 10 times. Okay, and so every observation is in the validation set basically exactly once. There's no overlap between the validation sets, and all of the different validation sets form the entirety of your data as well. Okay, so we can do this, and so here we will take our data, and again, here's our Olympic data. I have a total of 28 observations. Okay, 28 observations. So I can do, say, 4-fold cross-validation. If I do 4-fold cross-validation, then I will have 4 chunks of 7. Okay, and during each iteration, I will take 21 observations, train my model on 21 observations, meaning I will pick the slope and the intercept, or the other coefficients based on those 21 observations, and then I'll get that line of fit, and using that line of fit, I will now measure how well does that line of fit predict the 7 points that I left out. Okay, and I repeat that process 4 times. And so the next few slides will illustrate kind of what this k-fold cross-validation process looks like for this data set. Okay, let me go ahead and give you your third view quiz answer. Third view quiz answer is the letter A. A as in apple. A as in apple is the third answer. Okay, third answer is A. Okay, so here is all 28 observations, and I'm going to just randomly partition this into 4 chunks of 7. Okay, so randomly 4 chunks of 7, and what we will do is for each of our kind of folds, okay, meaning we're fitting the models on 21 observations, and we're going to use that fit in line to predict the remaining 7 observations. Okay, we're going to try fitting a whole bunch of these different models. So one, I will fit a linear model, a straight line model. Then I'll fit a quadratic model, a cubic model, 4th order, 5th order polynomial. And then just for fun, we will also try an 8th order polynomial and a 17th order polynomial. Okay, so when you have 21 observations in your training data, if you have basically a 21 order polynomial, you could fit all of your things like perfectly. You run out of degrees of freedom, but So that, that creates its own problem. But, we can fit a 17th order polynomial, which would be like very wiggly, and we can try to fit our data as close as we can. But basically, once we have that line of fit, we're going to look at the 7 observations that we leave out, and we're going to kind of measure our error there and calculate that, okay? And we're going to find the cross-validation score by kind of averaging the squared error for each model, okay? So this is how I'm going to split our data into 4 different sets, okay? So I'm doing this manually, okay? And I just kind of want to say, in real life, we would not do this manually, okay? And if you're taking like my class 101C, I show you like packages and functions that will do this kind of cross-validation and k-fold business for you automatically. But here I'm doing it manually so you can kind of see the code and kind of just see the process manually. And I would say that's a lot of the emphasis of this class, is you understand the actual mechanics of each of these things. And I'm going to force you to write like manual stuff in your homework and things, so you actually have to kind of build the machine by hand here. Okay, so here I'm just taking, I've got 28 observations, sampled. What that does is it shuffles the order of those 28 observations. And then after I shuffled those 28 things, I'm going to put the first 7 in set A, the next 7 in set B, the next 7 in set C, and the last 7 in set D. And I'm going to gather those together in a list and call that our sets. Okay. And then I'm going to, because I know I'm going to fit each of these things 4 times, I've got 4 folds, I'm keeping a place of where I'm going to store the cross-validation errors. Okay, so I'm going to have, and I know I'm going to have 4 values for the linear model errors. I'm going to have 4 values for the quadratic model errors. And right now I'm just leaving them all as NAs, and I'm going to just fill them in as we go through. Okay, and I don't want you to be intimidated by this code, but basically I'm going to repeat this process 4 times, okay? And so I'm going to just do it for set 1, set 2, set 3, set 4, okay? And I'm going to go to my list, okay, where I have the 4 different sets here, and I'm going to say, okay, for our first iteration, we're going to select set A. Set A, again, is just the 7 random observations, okay? And I'm going to say those are going to form my validation index. So maybe it's observation 6 and observation 18 and observation 3, but I'm going to have 7 observations here. And we're going to remove those observations from our x variable, year, okay? And so after I remove those 7 observations, the remaining 21 observations are in training x. I remove those 7 observations from our y variable, time, and that's going, or our t variable, our target variable. And so those 21 remaining observations will be my training t values, okay? The 7 values for x will be my validation x, whoops. And the 7 values for y will be my validation t, okay? I gather my x and t values together into a data frame. I call that the training data frame. Here I gather my validation. These are 7 observations here, and that forms my validation data frame. Okay, so my n is going to be 7 in this situation. And I'm going to fit model 1, which is a linear model, where I'm fitting it using the training data. Now that I have, so this is going to store, say, the slope and intercept in the linear model. And now that I have this slope and intercept form, I'm going to say make predictions using that model and make predictions for the validation data. Okay, and so these will be my t hats. Is this okay? I want to make sure. All right, and then we're going to take the difference between the actual values in the validation set and the predictions that I just made here. I'm going to take that difference, I'm going to square them, I'm going to add them up, and divide by n, which is 7. I repeat the process, but this time I'm going to take my observations t, okay, predict them using a second degree polynomial, poly x2. Okay, using the training data, I'm going to get the slope, the intercept, basically a W0, a W1, and W2. I'm going to use those parameters to make predictions on the validation set. That's going to be my t hat 2. I'm going to take the difference between the actual values and the t hat 2s. I'm going to square that difference, add them up, divide by n. Okay, and basically this is all the same code, but I'm going to do it for third order polynomial, fourth order polynomial, fifth order, sixth order, fifth order, eighth order, and 17th order polynomial. And I just kind of repeat this. And I'm going to do this a total of 4 times. Okay, so just so you can kind of see what this looks like, this is all 28 observations. These red dots, there's 7 of them. That's one of my validation sets. I think I just arbitrarily picked validation set C. Okay, so what we're going to do is we're going to remove those 7 data points. Okay, so those 7 data points are removed. On the 21 remaining dots, so if you count these, there's 21 remaining dots, I fit the linear model. Okay, I fit a straight line model to these 21 data points. And now I bring back those 7. So if you look, I'm going to bring back these 7 dots here, and this is the exact same line. And I say, okay, so this is the line that was fit on the 21. I say, here are the 7 red dots. How much error do we have? Okay, and so the mean squared error on this particular validation set is 0.0319. Okay, for a different validation set, we're going to have a different error, different mean squared error, and for we're going to have a total of 4 of these things. I just have one of these things right? So some of the dots got predicted by the line really well. Some had a bit more error, and so the mean squared error for this particular validation set is 0.0319. Okay, is that okay? This kind of process here. I repeat the same thing again. Here are all 28 observations. We're going to hide the red dots, and we're going to fit a quadratic model. Okay, so this is for these 21 dots here. This is the best fitting quadratic line. Okay, now I bring back the red dots, and I say, how well does this quadratic line predict these red dots, right? So here's the original. So those red dots are in the exact same position. And we're just saying, how well does this quadratic line predict these dots? And so I calculate the mean squared error for these dots, and we get 0.025. Okay, and I mean, it's hard for me to kind of judge, but looking at these dots and these dots, I don't know. I guess this one's doing a slightly better job. 0.025. Okay. Same thing, we're going to do a cubic line. Okay, so again, we remove the red dots. Here's the cubic line. We bring back the red dots. And we say, how well does it fit? How well does it fit? And the mean squared error here is 0.0131. Okay, so so this is what we have so far: linear, quadratic, cubic. And here's a 4th order polynomial. After removing these, this is what we get. We bring back the red dots, and we measure how much error we have. We have 0.0192. Here is the 8th order polynomial. Okay, so the 8th order polynomial is really able to kind of accommodate this one kind of outlier pretty well. And you can see by having a higher degree polynomial, we get a little bit more of waviness, which I guess may or may not be a good thing. We're shrinking the amount of error on the training set, okay? But then when we bring back the validation set and we say, okay, well, how much error is there? We say, oh, you know what? It's actually starting to get bigger at 0.02, okay? And then, it becomes almost laughable when we do the 17th order polynomial. Okay, so when we do the 17th order polynomial, it's this very high, we're basically raising x to the 17th power. And so you can see, like, if you go from, say, 2 to the 17th power to 3 to the 17th power. It's a huge difference, right? And so this, you get these like super steep curves here. Sure, it is fitting this data very, very well, these data points very well, and we've really shrunk down the amount of error here. But how well does it perform on the data points that I left out? Okay, so I bring back the red 7 red data points that I left out, and we say, oh, you know what? This does a comically bad job of 1,640. Okay, whereas everything else was like 0.02 or 0.01 or 0.013. Okay, but it's the same kind of thing. Here are the dots. We leave those out, fit this line. I bring those dots back, and we go, oh, you know what? We did not do a good job. Okay, we did not do a good job on trying to predict these red dots here. Okay, so this is what our cross-validation score looks like. So remember, I kept track of all of these things. Okay, so for the linear model, I fit it to validation set A, and validation set B, and validation set C, and validation set D. I repeated the process 4 times. I got 0.0224, 0.0258, 0.0319, and 0.1896, and the average is 0.0674. What do you think is going on? Well, okay, then let's look at the quadratic one. Quadratic one, I fit it to my 4 data sets. Okay, 4 different folds, right? We train it on 21. We predict the 7 that were left out. And we get 0.0253, 0.0371, 0.0250, 0.1625, and we get 0.0624. And we have 0.04 for the third order cubic one, 0.046, 0.029, 0.013, 0.140, and we get 0.057, right? So I think the ones that we illustrated were validation set C, and we saw this, okay? And so we see this kind of interesting thing happen. And then for the 17th order one, we have 91.3, 291.3, 1640.92, and 77.87, okay? And so the overall cross-validation score, when you average all 4 of these things, you get 525, okay? Now, so if we look at the overall average, the 8th order polynomial has the lowest average cross-validation score of 0.0419, okay? And then the 3rd order polynomial has the second lowest of 0.0571, okay? So if we went strictly off of cross-validation score, we'd go with the 8th order one, okay? But I would probably say the 3rd order one is a little bit better. One thing that is kind of responsible for the fact that the 8th order polynomial seems to be the best performing one is that on validation set D, its score is 0.08 versus the other ones are 0.168, 0.166, 0.140. What do you think is going on? Why do you think validation set D is so much higher than validation sets A, B, and C? Any guesses? So here's the original data. Okay. And validation set C are these 7 red dots.
The variation of set D is a little bit lower than others.
What do you think? What is special about validation set D? What do you think? What would throw off our analysis here? It's this one observation out here, okay? It's this one observation, the 12 seconds that was measured back in 1896, where I don't know what kind of stopwatch technology existed in 1896, but they said the fastest winner was 12 seconds. And so, when you look at all of these things that are fit, right, and you're trying to fit this, okay, you got this huge kind of leftover residual, right? and you try to fit this, you get this huge leftover residual, and it's like only until you get to like the 8th order polynomial, right? On the 8th order polynomial, now the amount of residual for this one leftover dot is like way smaller than everything else, right? Okay, so that's kind of what's going on here, is that all of these, that one weird dot, that outlier, is showing up in validation set D, and so therefore when you're measuring the squared error, which really punishes big errors, right, much more heavily, right? So least squares regression really hates outliers, okay? And that's why I think in 101A you should have gotten all these warnings about outliers and leverage points and all that kind of stuff. Okay, so that's what's going on. It's really kind of throwing our thing off, and for whatever reason, our eighth order polynomial just gets it right, even though it was left out in the training set. It kind of gets it right, and it does that. Okay, so that's a limitation. So k-fold cross-validation, in almost every way, I would say, is superior to leave one out cross-validation, okay? You should almost always do k-fold cross-validation instead of leave one out cross-validation. But one of the limitations of k-fold cross-validation is it is highly dependent on the random folds, right? So here I just shuffled up our 28, I don't know where this code went, okay? I took our 28 observations and I shuffled them up and I put 7 into each of these things. If I did this process again, I changed my set seed, then the 7 observations that end up in sets A, B, C, and D would all be different. And my analysis, the results that I get here, could end up being quite a bit different. So here, when I ran it and you saw the pictures, it turns out the 8th order polynomial has the kind of lowest CV score. Here I ran the exact same code and the same process, but here I just changed the starting seed so that the 4 different folds that we get of 7 observations ends up being different. And here we see a little bit more what we expect, a little bit more in line of kind of our classical approach, where the 3rd order polynomial has the best performing fit, and the 8th order polynomial does not do a good job, okay? And if especially if you look at validation, again, validation set D happens to have the, weird outlier point, and I don't know, 17th order polynomial, something crazy happened, 53,000 or whatever, it doesn't really matter, right? The 17th order polynomial is just kind of a joke anyway. But we can see this ended up way bigger, and so its cross-validation score for the 8th order polynomial is way off, right? Okay. So the 3rd order polynomial here now performs the best, and here I did it one more time, just kind of changing the set seed, okay? And here we see the 3rd order polynomial performing the best. And now the 8th order polynomial, kind of is, doing a little bit better and things like that, okay? So because of the randomness inherent to the process of k-fold cross-validation, it is possible, when you do k-fold cross-validation, it's possible to get a cross-validation result where a suboptimal model happens to perform best, right? If you only did this one time, you might say, oh, let's go with the 8th order polynomial, and that would be the wrong decision, okay? So that is one of the drawbacks of k-fold cross-validation, is that you could end up picking the wrong model because of the randomness involved. And so it is often recommended that you would do k-fold cross-validation multiple times. You would do multiple repeats of k-fold cross-validation, and hopefully, like if you run it 5 times or something, you repeat it 5 times, you'll get kind of a plurality or a majority vote, right? Like if you do it 5 times, maybe 3 of them will say the 3rd order polynomial is the best, or 4 of them will say the 3rd order polynomial is the best, and then maybe 1 of them will say, oh, the 8th order polynomial is the best, okay? But because you ran it 5 times, you can say, okay, overall, it seems like the third order polynomial seems to be the best performing one out of my 5 repeats here, and therefore that's the one that I'm going to go with. So that will help kind of corroborate your decision. But again, all of these things require computational energy, okay? And so it, if you're able to afford that computational expense, it's recommended to run cross-validation more than one time. Okay, does that kind of make sense? And again, this was a very manual process. In real life, you would probably use one of these automated packages. So one of them is cv.glm. In 101C, at least when I teach it, I teach using the Tidy Models framework, which has a whole set of tools that are really great, but that's like a whole nother learning curve, and actually it's like in a whole course on introducing all of that stuff. So, within this class, we can say we'll use this function cv.glm. We've already seen cv.glm when we do leave one out cross-validation, and so that is the default, okay? And if you do cv.glm, there is an option for the argument k, and k will specify how many folds that you want to do. And so you can say k equals 5, and it will do 5-fold cross-validation or something like that. If you don't specify the k, then cv.glm will do leave one out cross-validation. And again, in general, leave one out cross-validation is not recommended. It is computationally too expensive and not the preferred method. Okay. That said, for your homework, you will code leave one out cross-validation by hand, and you'll kind of work through that process. Yes, question?
So is it like the number of folds?
A fold is, if you take your training data, you are dividing it into different sets. So the K is how many of these different sets or how many different folds, okay? So a fold is just how many divisions you're going to take your training data and split it up into. Okay, so this picture represents 4 folds. Okay, we've taken our training data, we split it up into 4 chunks. Each of those chunks or each of those sets will be the validation set, and then the other 3 will be our will be used to train or figure out the model parameters of the best fitting line. Okay, so fold is each one of these kind of divisions. Yeah.
Actually, there are several steps of the cross-validation. And the first step is we split the data set into 2 sets, the training set and the validation set. And actually, we assume that the 2 sets are independent. The data from 2 sets are independent. And actually, we fit a model by the training set, but data from the training set.
Yes. So that is 100% true. That is something I cover in 101C. So 101C is like the more practical application for like if you're doing. So let me do.
Yeah, what I'm trying to ask is, when the step after that, we have the optimization globally. We just like pulling all the data into the training set and pulling all the data into the validation set. And could that be a problem?
Yeah, that's generally not recommended because you are.
Just like in the leave one out CV, and we use the number 1 as the validation set and others as the training set. And actually, we have 4 laws at last, and we're pulling these 4 maybe CV value or the loss into the average, and we have the globally optimization. And at this stage, could that be a problem just like we have the correct answer and we take the final examination.
Yeah.
We use all the set to be the training set.
Right. Yeah, so in general, okay, so in practice, you are going to split your data multiple times. And so in practice, you start off with all of your data and you do an initial split where you have training data and testing data. And the testing data is really kept separate from any of the modeling process, okay? And then when you have your training data, then you split that further, and that's kind of what we talked about here. So here when I talked about k-fold cross-validation, really I'm just talking about now that we're in this phase of taking our training data, we're going to do one sample where we have 3 of these folds, and we're testing it on the fourth set that we left out, and this and that. Okay, and so that's kind of the process that you want. Your question is when after we go through and we pick out a model that we like, we should run it on this test set to see how we do. Are we allowed to kind of mix the test data back in the training data together to kind of get this whole overall performance? And the answer is no, you shouldn't do that. You should really just model it on just the testing data. And the name test is, I think, appropriate. The analogy I like to use is if you wanted to see if a student learned the content, you might give them an exam, right? And part of their studying, you might release practice exams. Okay, and so in the practice exams, there's different problems, and if the test, your final exam, consists only of questions on the practice exam, it's not really a good metric, because it might just be, did they just memorize the questions in the practice exam versus did they actually learn the concepts and are they able to answer questions that they haven't seen before? So usually you want on your final exam questions that these students haven't seen in the practice exam, okay? And so the question, so that's usually how we do. We do the testing that is completely separate from kind of the training, which is the thing of the practice exam. And so now there's kind of this question of like, okay, well, what if the final exam is a mix of like completely new problems plus like problems they might have memorized? And is that going to be a better metric than just completely new problems or something like that? And I would say the general consensus is keep the testing completely separate, but I don't know.
So the independence is a really important assumption here.
Yeah.
Because we need the validation set, we can regard it as a new sample we have from the population, and the training set is the sample we now we have, and we use them to feed the model. And what I'm trying to ask is, at the last page, we use the average of the loss. Actually, we are pulling all the data into one set.
So this is just this is during this part of kind of the cross-validation. Okay, so we're not doing, that's not part of this final testing thing. So
actually there are 3 sets, and the training set, validation set, and a test set.
Yeah. So in practice, this is, you would do an initial split, and then after your initial split, you're doing cross-validation on this kind of training data. Okay, and this is kind of the illustration. Here's a 3-fold cross-validation where we took our training data, we split them into 3 different colors, green, yellow, and blue, and then we train it on the yellow and blue and test on the green. We train it on the green and the blue, and we test on the yellow, and we train on the green and the yellow, and we test on the blue. Things like that. That's kind of the illustration here. And so when you're doing the averaging here, it's really just on this part, which is okay. But again, for the final model, you're going to do it on completely new data, new problems that you haven't seen. So it's kind of like, let's say, again, your professor releases practice exams, like multiple of them, and what you can do is you can you're going to say, I'm going to kind of practice I'm going to study like there's 4 practice exams. I'm going to study practice exam 1, 2, and 3, and then I'm going to kind of test myself on practice exam 4, right? And you might have done this for like your SAT prep or something like that. I don't know. Did you guys take the SAT or something, right? You buy like a book and it comes with a whole bunch of practice exams, and you during your studying, you're like doing this thing and this thing, and then you're like, okay, I feel pretty good. Let me try out this practice exam in the book. And you're hoping that practice exam in the book, you did well on it, and then you go to the actual exam, and you're hoping that it kind of goes like that, right? And so this kind of validation, this cross-validation thing is like, okay, we're doing like practice exams. We're like, we have like this whole kind of set of like practice questions per se. And rather than just studying all of them all at once, we're going to kind of like set some of these aside for like a practice test. And I'm going to study like these other questions or something like that. I don't know. that's kind of the thing. Let me just get back to this process. Oh, and let me give you I gave you 3 answers so far, I think. Okay, let me give you your fourth one. Fourth one today is the letter B. B as in bear. B is your 4th view quiz answer. B. And again, this is just some code that you could use. There's some kind of pre-existing code that does cross-validation for us, that does these kind of metrics and analysis for us, which in general, in practice, when you're actually doing things, you would use this. Again, in your homework, I kind of make you write code manually yourself, and my hope is that by writing it yourself, you're going to really learn this process, kind of the mechanics of the process. When you run cross-validation using cv.glm, here I'm doing 4-fold cross-validation. One thing that we notice is that I'm running the same command. The cross-validation score ends up being a little bit different each time, okay? And again, that is because of the random assignment of which observations end up in which of these folds, okay? And so there's randomness there. Whereas if you do leave one out cross-validation, okay, so here it is. So here's for the linear model, these are the 3 different scores. For the quadratic model, these are different scores that we get from repeating the process multiple times. Here are the scores that we get for repeating the process multiple times on a cubic model, okay? Whereas if we do this thing for leave one out cross-validation, we notice we get the exact same score every single time, okay? And that's because when you do leave one out cross-validation, there's no randomness there. It's always, every observation serves as a validation point every single time, okay? Whereas here I'm fitting the cubic model, and I ran it I have 3 different repeats of 4-fold cross-validation, and my CV score was 0.049, 0.064, and 0.07. So we're getting, a decent amount of variation from one repeat to the other. All of these times we're doing 4-fold cross-validation, but we're getting different things, okay? Leave one out cross-validation, you are not going to get any kind of variation there. All right, so I just took some of this from Wikipedia, but cross-validation overall is a method to see how a particular model will generalize to new data. The goal of cross-validation is to test the model's ability to predict new data that was not used in estimating, and that's going to help us avoid problems like overfitting. We don't want this situation where we have fit our training data perfectly, okay, but this pattern that we've established here just doesn't generalize to unseen data, right? If our only metric was minimize the squared error, we might be tempted to say, hey, this model does really good because it predicts all of these data points really, really, really well. okay? But the truth is, oh, you know what? It doesn't generalize really well to new data points. So that's gonna, cross-validation helps us avoid that kind of situation, okay? Multiple rounds of cross-validation are performed using different partitions. The validation results are combined. And then we do multiple repeats of cross-validation itself to kind of help smooth out the different issues of having randomness. Yes?
Does it ever make sense to select the capable clusters?
So you might want to do like when you do your initial splits or something, if you're doing like in time series data, where you don't want it random, where generally you want to kind of predict future things. So rather you kind of look at your training data will be like the past up to like the last, maybe you leave out the last couple of years and then you say, how well can I predict the last couple of years if I'm, kind of blind myself to those things. And then that might give you an indication for predicting the future. But in general, you want to keep it random because there could be, because if there's some kind of correlating thing related to the order of your values, then it's going to kind of trip up the models that get fit. So in general, you want randomness. Yeah. Okay, that is it for today. We'll wrap it up here. Have a great weekend. Good luck on your homework, and we will see you on Monday.